news that I want to share with you. And the second part of my title is, what are the next steps? So I have two messages to tell you about today. One is to describe the impact of the nutrient reduction in Narragansett Bay. And two is to suggest that there's some further nutrient improvements that may be possible. Currently, the implementation of advanced wastewater treatment has reduced the nutrient input to the bay by over 50%. And it's been a huge success in decreasing the upper bay hypoxia in the summertime. It's not a total success yet in terms of completely eliminating hypoxia, but it's been a huge, huge improvement. So before the nutrient reduction, many areas of the upper bay, Seekonk River, Providence River Estuary, Ohio Ledge area, Greenwich Bay, and a tongue down toward Quonset, had extremely low oxygen values during the summertime. The dark red here is less than 1, the lighter orange is less than 2, and you can see that there's very large areas of the bay that were impacted during these events. And some of those events caused massive fish kills, like this one in 2003. What you see floating here are menhaden fish, but there were other dozens of species of fish and invertebrates which were dead on the bottom. And I thank Christy Acutis for this picture. The managed nutrient reduction was implemented in 2005, and it's actually still ongoing. They're still building another big reservoir to capture storm drainage. But most of the reduction, the above 50% reduction was completed by 2012. Here's the timeline that was proposed, and they struggled to get the first reduction in 2005. This is from 11 wastewater treatment facilities that directly input their waste to the bay. And that first 30% reduction was accomplished in 2005. The second reduction, which was the 3 big wastewater treatment plants on the Providence River, reduced their inputs by 2012. It's not shown on this slide, but that's actually when it happened. And since then, the nutrient reduction of greater than 50, actually almost 60%, has been achieved. That resulted in a decrease in the dissolved inorganic nitrogen in the bay, which is the major limiting nutrient. This is dissolved inorganic nitrogen on the y-axis, and this is a gradient of stations down the bay from the Providence River to Rhode Island Sound. And I've colored these bars in bright blue for the survey prior to the nutrient drawdown, and the most recent survey in 2014 after the nutrient drawdown. So you can draw your eye to see how much the reduction has been. In Fields Point, the first station there shows a huge reduction. Bullock's Reach, a significant reduction, and so on down the bay. All the way down to the Graduate School of Oceanography, you can still see there's about a 50% reduction there. And even out into Rhode Island Sound, there's a reduction. There are some areas that are still in trouble. Greenwich Bay is improved greatly, but it still has significant hypoxia in the summertime. And Mount Hope Bay is largely in Massachusetts, and they don't have the same regulations that we have in Rhode Island. So the reduction there is not complete, and they are still suffering from some hypoxia. It's not severe, but it does happen. That reduction in nutrients caused a reduction in primary production. It was about 300 grams carbon per meter squared per year, and it dropped by about 100 grams carbon per meter squared per year, 1/3. And you can see that this period during the nutrient reduction from 2006 to 2011, much of the bay was bright green in color: the Seekonk River, the Providence River, the Ohio Ledge area, the Greenwich Bay area. The same areas that suffered low oxygen had very high productivity, greater than 1 gram carbon per meter squared per day. You can compare that to after the nutrient reduction in 2013, and now almost the whole bay is bright blue with primary production rates less than 1 gram carbon per meter squared per day. In fact, more like 0.5 gram carbon per meter squared per day. And it goes right from the mouth of the bay to the Ohio Ledge area that this improvement in the bay is very noticeable. People have exclaimed to me over how clear the waters are. whether you're in the Ohio Ledge area, the Mount View area, or Mount Hope Bay. So it's not just the nitrogen species that have been decreased, as shown here, total nitrogen, ammonia, nitrate, but also phosphate. And this is a different process. This isn't one that's governed by the wastewater treatment plants. This was due to the fact that freshwater ecologists could attribute eutrophication in freshwater areas to phosphorus inputs. So they mandated that phosphorus be taken out of detergents. That's a very major part of the wastewater stream, detergents. So taking the phosphate out of detergents meant removing it from the wastewater stream and thus input to the natural systems. So we can, and this started in the 1990s, well before our reduction in nitrogen in Narragansett Bay in 2005. But it's been going steadily on for that whole period of time, 1990s to the present. And in fact, just about the same reduction has been achieved with phosphorus as was achieved with nitrogen, about a 50 to 60 cent per reduction in input to the bay. So the two nutrients have gone down in tandem. They're both limiting nutrients. Most often the limiting nutrient is nitrogen. The impact of reducing the nutrients and reducing the primary production has caused the hypoxia index to improve greatly. The black bar here and the red bars are prior to the nutrient, is prior and during the nutrient reduction. The bright green bar is after the nutrient reduction. And in almost every case, Bullock's Reach, North Prudence, Greenwich Bay, Sally Rock, Mount View, the mouth of Greenwich Bay, you can see there's been significant improvement in the hypoxia index. Papa Squash in the Upper East Passage has always had limited hypoxia. Now it's almost vanishingly small. Quonset Point used to have a little bit of hypoxia, and now it has none at all. As I've told you, Mount Hope Bay still has a problem. This is a seasonal cycle of the dissolved inorganic nitrogen and phosphorus on your left-hand side, the middle and bottom panels. And this is to show you the seasonal cycle from January to December, that the reduction in nutrients is year-round. It's not just the summertime period. The reduction is mandated for the summertime period. They have to achieve that at each of the wastewater treatment plants. But to keep the bacteria healthy, and it's also imposed on them that they should maintain the levels as low as possible throughout the seasonal cycle, the actual reduction goes on year-round and not just in the summertime. Hypoxia is not a problem in the wintertime. The cold water of wintertime holds a lot more oxygen than the summertime, and plus the rates of respiration are much lower. So we only have a hypoxia problem in the summertime, but in fact, the nutrients have been reduced year-round in the bay. And you can see that this reduction from January to December for dissolved inorganic nitrogen and for dissolved inorganic phosphate is on the order of 50% to 60% year-round. Now, I told you that the nitrogen reduction and the phosphorus reduction were by two different methods. And you might worry that that might lead to strange ratios of limiting nutrients in the bay. If they're out of phase with one another, and you're apt to get harmful algal blooms or other strange things blooming. But in fact, the nitrogen to phosphorus ratio shown there in the lower right has remained about the same. It was about 6 prior to the nutrient reduction in the 70s and 80s, and it's still about 6, indicating that throughout this period, the ratio has not changed and that the primary limiting nutrient has been nitrogen. So are there options for fine-tuning nutrient reduction? And I'm suggesting that we could release nutrients from the wastewater treatment facilities in winter. As I've said, the process goes on year-round, and we actually only need it in the summertime. And the rationale for that is that a major wild fishery in the bay is the quail fishery. The year-round nutrient reduction has reduced the quail yield from the upper bay, about an area of maybe 10,000 acres or so. In recent years, over 20 million coal hogs with a value of $5 million have been harvested annually from the bay. And since the nutrient reduction, the coal hog production has declined by 35 to 40%. So a first step might be to work on restoration and improvement to this area of the fishery. Recent literature indicates that most coal hog growth occurs in the spring and in the fall after diatom blooms in the Northeast US. The URI Sea Grant mesocosm experiments, which we've been conducting over the past 2 years, further suggest that the winter-spring diatom bloom enhances the reproductive potential of hard clams. And my colleague, Mike Potter, is going to tell you about these experiments after I finish speaking here. Thus, I think a management option to consider is the release of nutrients from Narragansett Bay Commission's big 3 wastewater treatment facilities on the Province River to support a winter-spring bloom in the upper bay when summer hypoxia is not a problem. And the argument in favor of this is based on 2 major storms years that we have had in recent years. Both of these storms put a lot of nutrients in the bay. First one was the flood of 2010, which I'm sure a lot of you remember. And the second, which you probably don't remember, is the major, huge winter-spring bloom that occurred in 2018, which was based on a series of small storms through the winter and late fall period, putting in nutrients to the bay. So this is a dissolved inorganic nitrogen graph in the top panel here from prior to the nutrient reduction to more or less the present. And the flood of 2010, in some stations, there were up to 19 inches of rain. And this is a late March, early April event, well after the winter spring bloom, which was also major that year. And the second event was the winter spring bloom of 2018, based on a series of storms through the fall and early winter, which put up to 17 inches of rain into Rhode Island at some of the stations. And if you look at the dissolved inorganic nitrogen record for 2010, you can see that as the first reduction caused a decrease in the nitrogen in the bay, the standing stock, the flood event raised that amount from about 4 micromole up to about 14 micromole. So well above the period before the managed nutrient reduction. And to a lesser extent, these storms of 2017 and 18 also increased the nutrient concentration in the bay from about 4 micromole up to about 8 micromole. And this increase in nutrients was throughout the bay. The top panel is the average. The second panel is the upper bay, mid bay, and lower bay. Much less effect in the lower bay, as you might expect. And in some of the embayments, we also saw major effects of those storms. The Providence River has both peaks very prominently. The Greenwich Bay and Mount Hope Bay both also record these events. So this is our long-term record of winter-spring blooms in Narragansett Bay from the GSO dock, Graduate School of Oceanography dock. And this is the signature event in the wintertime when we experience a huge bloom of diatoms, which, because it's the coldest part of the year in January and February, it's largely ungrazed. This pulse of organic matter goes to the bottom, and it feeds the bottom community through the rest of the cold months and into the warm months. And you can see from this record that major blooms are very seldom, 77, 86, 96, 10, and 18. But the 2010 flood, it was prior to the flood that we also had a major bloom, and I can't separate the fact that bloom from the later flood bloom that came just after, and which you can also see recorded there. And also the huge bloom of 2018, the best winter spring bloom we've ever experienced, 35 micrograms of chlorophyll per liter. So these were huge pulses of organic matter to the bay in the cold months of the year. And those those storm events did have year-round impact on primary production. The 2010 flood increased the primary production from something less than 200 grams carbon per meter squared per year up to about 230. The thing about this flood event was it was such an intense event that it caused a very rapid flushing rate in the bay. So the impact of this huge storm was actually somewhat less than the series of lesser storms in 2017. So in 2017, 2018, we also see an increase in primary production, which goes from about less than 200 grams carbon per meter squared up to something like 230. And you might worry that these pulses of organic matter to the bottom would have an impact on summertime hypoxia. Lindsay Field has shared her data with me on sediment oxygen demand in the top panel there. And we can see 2010, this is the summer of 2010. I've contrasted it with the summer of 2011. And 2010 is indeed a little higher, but it's not significantly higher, and it didn't cause any significant increase in hypoxia. It is the case that the ammonia release in 2010 is a great deal higher than in 2011. And this sustained the primary production through the summertime period of that year. So the effect of the storm did last several months into the summertime period. The nutrient release during these colder months did not cause an increase in the summer hypoxia, not the 2010 flood period nor the 2018 storm events. This is a graph of the days of hypoxia summed over the entire bay for every station. And the x-axis here are the time period from 2001 to 2018. The black bars are the days of hypoxia. And you may be interested to see that during rainy years, which is shown on the right-hand axis here, and the gray line, these are the years that caused the most hypoxia: 2006, 2009, 2011, 2013, for examples. However, if you look at the black bars for 2010 and 2018, they are not any greater than hypoxia in non-rainy summers. So it may be the case that this pulse of nutrients that comes in the colder months due to these storms has an impact on the fisheries. And I was able to look at two of them. We have a survey at Fox Island, and this is the trawl data from that survey for squid from prior to the nutrient reduction, during the nutrient reduction, and after. And you can see there's a trend downward in our squid catches as the nutrients are reduced. There's a pretty good correlation there. You can also look at the storm year 2010 and see it's about the same as the period 2005 to 2012, the period of the nutrient reduction. And squid have 1 year to grow before they're harvested. So a stimulation of the squid would show up in the succeeding year, 2011. And it apparently does here. We have a much higher red bar in 2011 than we do in 2010. That did not happen in the series of storms happening in 2017 and early 2018. The amount of squid has continued to decline somewhat in the bay, and we would expect a pulse of squid production in the year following in 2019, and that didn't happen here. And this is after the big 3 wastewater treatment facilities on the Providence River have mandated their nutrient reductions. We also looked at hard clam landings, the quahog landings, in a similar manner, and we see a somewhat similar pattern in that after the nutrient reduction, we see a decrease in the number of clams harvested. And the 2010 harvest was about what you would expect for 2005 to 2012. And it takes 3 years at least to harvest quahogs after they've spawned. So we looked at the year 2012 to see if there had been a pulse in the landings for quahogs in that year. And indeed, it does show up here just as it did for squid. And also similar to squid, it does not show up after the 2018 storm. So it looks like in this case, in both cases, that The 2010 flood did result in increases in the squid and quahog fishery, whereas the 2018 massive winter spring bloom did not. So in summary, the managed nutrient reduction has decreased the nitrogen to the bay by over 50%. It's actually almost 60%. And this has the impact of decreasing the primary production. The objective of the managed nutrient reduction was to decrease summer low oxygen in the upper bay, and that was super successful. Days of hypoxia have been minimal since 2013. On 2 occasions in 2010 and 2018, the storm nutrient input during colder months reversed the managed nutrient reduction. The more extreme flood year of 2010 had a greater input of nutrients in 2018, but less of an impact on chlorophyll levels due to the enhanced flushing rate in the more intense storm year. While storm nutrient impacts extend over the year in terms of primary production and benthic nutrient release, summer low oxygen was not increased. This is a wonderful result of this natural experiment. The storm nutrient increase did appear to enhance some fisheries. Squid biomass increased in the year after the flood. Clam recruitment tended to increase 3 years after the 2010 flood year. However, neither fishery increased after the 2018 major winter spring bloom. The reduction in nutrients from the Providence River wastewater treatment facilities after 2012 reduced bay nutrient concentrations, perhaps reducing clam condition and squid condition, and perhaps causing recruitment failure. These results suggest that the managed nitrogen reduction may not be as necessary and beneficial in colder months as it's been in warmer months. And I further suggest that we could release nutrients in the wintertime, and it might have a beneficial effect on wild fisheries and aquaculture in the bay. Thank you very much.
Great, thank you so much, Dr. Oviatt. I guess now will Michael be following up with you?
Yes,
okay.
Mike will follow, yep.
Okay. Perfect.
Okay, hello everybody. I'm truly excited to talk about our current research on the response of the hard clam mercenaria to a changing Narragansett Bay. So the reason why we looked at the hard clam for this experiment is it's a commercially and culturally relevant species to Rhode Island's history, and it's currently as well. And it's a benthic filter feeder, so it relies on the settlement of phytoplankton in order to survive. Now, the idea behind this experiment was to look at how the nutrient reductions impacted this species, as well as future warming waters caused by climate-driven change. And the hypothesis here was that as temperatures increase, winter spring blooms would be decreased, so there'd be less food for the clams, and this would impact their recruitment or their reproduction, their condition, a metric of their general health, and their growth. So warming waters in Narragansett Bay are expected to reach 3 to 6 degrees increase by the turn of the century, and temperature and food remain the primary factors that control the biology of these animals. And the winter spring bloom is a very important food store for these animals in the winter months and into the beginning of the warming period in spring. Another part of this experiment was looking at the history of the sediment within Narragansett Bay. Around the Providence River estuary is where we chose to locate our experiment, and that has a history of pollution from industry, from hydrocarbons to heavy metals, things of that nature. And we also chose a secondary site more towards mid-bay, which has more pristine, less polluted sediments historically. Now, this experiment was done in mesocosms. You might not know what a mesocosm is, and you might wonder why we chose them. Mesocosm is an ethical and controlled, often simplified model, which is used to examine the direct influences on ecosystem dynamics. Our lab, the Marine Ecosystem Research Lab, was established in 1976 following the passage of the Clean Water Act, and has done 30 plus years of research using these experimental models. Many of these are long-term experiments that are 1 year or longer. They look at things like biological and chemical cycles, as well as environmental thresholds to external factors like heavy metals and hydrocarbon pollutants, and more recently, climate-driven warning. This photo here on the right actually is a picture of Merle as it was being built. It operated cylindrical mesocosms that were 5 meters deep for the duration of its experiments. Now, looking at the winter-spring bloom's relationship to temperature, chlorophyll A is often used as a proxy for primary production in the water column or production through phytoplankton. And the winter-spring bloom is noted by a chlorophyll A measurement, generally between 10 and 20 micrograms per liter. On the y-axis here, you'll see chlorophyll in micrograms per liter, and with temperature as well. And on the x-axis, we have time. Now, winter-spring phytoplankton blooms occur when temps are at or below 3 degrees C, when zooplankton and filter feeders are suppressed by the colder temperatures. Above this temperature threshold, blooms are notably diminished or fail to occur at all. So if you look at this graph, the red line is temperature and the green line is chlorophyll. And here we are in January. If you look at chlorophyll, it's pretty low. It's definitely not a bloom. And if you look at temperature, it's above that 3-degree threshold. As it decreases beneath it, chlorophyll then shows an increase, which indicates a phytoplankton bloom. And this continues as temperatures are low. This phytoplankton settles out. Temperatures remain low. We have a secondary bloom measurement here. And then as temperatures increase, you see an inverse relationship with high temperature and low chlorophyll measurements as we move into the summer months. And then you can see it, the gap here is quite large. We have lower chlorophyll numbers while the temperatures are very high. Now, looking at our model in particular, our experiment consisted of 3 temperature treatments. We had an ambient temperature throughout the year for the Providence River estuary. We had a cold treatment, which was 3 degrees C colder than this, and we had a warm treatment, which was 3 degrees C warmer than this. This was a way of looking at the past colder temperatures and our future warming temperatures towards that 3 degrees C increase threshold. Each temperature treatment had 3 replicates, so 3 mesocosms per temperature treatment. 1 tank with sediment, without sediment or temperature control was used to kind of gauge other influences on the system. So the system consists of 10 mesocosm tanks, 9 were used for the experiment, and 1 was used to kind of see what was going on if we didn't control anything. Now, on the left here, you can see a schematic of our mesocosm. It has a sediment tray, which has a large grab from the Providence River estuary, which helps establish our ecosystem. This red line here is raw seawater coming in directly from the Graduate School of Oceanography pump house. We have a paddle wheel, which mixes to prevent stratification, and then a heat exchanger, which allows us to control the temperature, make it colder or warmer. And in the bottom right corner of this photo, you can kind of see our different temperature treatments: yellow for ambient, blue for cold, and red for warm. The next photo here to the right is just a picture of the system as a whole. And then if we look at the rightmost photo, you can see down into one of these mesocosm tanks. At the beginning of the experiment, you see this rectangle here is a large sediment grab that came from the Providence River estuary, and then a smaller little container that has sediment that houses our clams, which is connected to these ropes so they could be removed at will. There were 40 clams per mesocosm with 120 per treatment and about 360 for the experiment. Now, the site selection, like you heard me talk about earlier, was kind of important. We chose 2 sites. One was here in the Providence River estuary, north of Connecticut Point, which has a history of pollution from industry. And then we had a secondary site for our year 2 experiment, which was taken here at the Jamestown Historical Sediment Recovery Site, which has a lesser history of pollution. And these experiments ran for year 1 with the Providence River sediment that the clams were housed in 2021, and then the mid-bay sediment in 2022. Now, moving from our site location, we'll take a look at how the temperature was controlled throughout the duration of both experiments. The temperature treatment of each of mesocosms refers to both the temperature and the nutrient profile of each treatment. Now that's very important because in the first year, 2021, you can see it here on this leftmost graph, we have temperature on the y-axis and then a date range on the x-axis. We unfortunately did not have temperature control until April. We started our experiment in March. So in lieu of this temperature control, stepped nutrients were added to each treatment in order to stimulate or simulate what we might expect a bloom to look like at the different temperatures. So in order to achieve this, we added 4 times the Bay average amount of nutrients to our ambient tanks, twice that amount to our cold tanks, and nothing to our warm tanks. This would show for the cold tanks a large phytoplankton bloom we would expect. For the ambient tanks, an average phytoplankton bloom around 10 to 20 micrograms per liter, and in the warm tanks, no bloom. Once these desired, sorry, skipped ahead. Let's see. Once the desired bloom levels were maintained for 2 weeks or so, a standard 8 times the Bay average was added in nutrients to each tank in order to more accurately reflect the nutrient profile of the research location. So if you look at these 2 graphs, this is our temperature profile over both years of the experiment. You can think of them as one continuous if you like. Our cold treatments are in blue, our ambients are in light blue, and our warm treatment is in red. And that tank that was our null tank that didn't get any treatment, we just kept it to see how things would react, can be seen here in black. Now, in our year 2 experiment that started in January in 2022 on this graph here, we did have temperature control the entire time, so the same nutrients were added to each mesocosm regardless of the treatment, so all could be treated exactly the same. A nutrient-driven bloom was attempted from January to March 22, but failed to occur due to excessive algal growth on the tank walls. Now, from there, we'll take a look at the primary production. Once again, chlorophyll A is used here as a proxy measurement for primary production that occurs within the water column. This would be from phytoplankton. We have 2021 here on the left and 2022 here on the right, with chlorophyll being on the y-axis and the date being on the x-axis. Now the 2021 graph shows a strong bloom in the ambient tanks in the light blue, and an even stronger bloom in the cold tanks in March and April when we were doing our simulated blooms with nutrients. And then notably, there was no bloom that occurred here in chlorophyll in the warm tanks, showing that this nutrient stimulation worked as expected. This trend does not follow into the 2022 experiment due to excessive growth of macroalgae on the mesocosm walls. One bloom of varying intensity event can be seen in a single mesocosm of each treatment. So we have one here in our null tank, one in our cold, one in our ambient, and one in our warm. Now, this is just looking at primary production within the water column. I did say we did have primary production occurring on surfaces within the tanks. So we'll take a look at the entire system's production versus respiration on this graph here. Now, this graph demonstrates the difference in methods of primary production between the year 1 and year 2 experimental ecosystems by looking at the production and respiration of oxygen. So we have oxygen production here on the y-axis in grams of oxygen per meter squared per year. And we have temperature treatment on the bottom. Now this isn't a gradient of temperature. We have our cold treatment here at -3 for year 1 and year 2, our ambient at 0 because that's our baseline, and then +3 for our warm treatment here. Let's see, primary production between the 2 experiments was quite different. You can see this just by looking at the lines here. Primary production is denoted by the green triangle in year 2021, that's here, and the green diamond in 2022. In the first year, where primary production was dominant in the water column as phytoplankton, the highest primary production was observed in the cold treatment and the lowest primary production in the warm treatment. You can see it here in our cold treatment and our warm treatment. Conversely, in the second year experiment, where primary production was dominant on tank surfaces with macroalgae, this showed the highest production in the warm treatment and the lowest production in the cold treatment. Now, the difference in respiration, which you can see here, respiration and primary production are almost equal in year 1, and in year 2, the primary production was greater than respiration, may be explained by our flushing rate, which is 20% per day, as phytoplankton can freely exit the system while macroalgae remained anchored to wall surfaces. Now, this is just how the system responded. Now we can look at the clams themselves. And our first metric that we wanted to look at was how their reproduction would be impacted. And for that, we developed 3 qualitative stages for a gonad. Their definitions can be seen here. We'll talk about them a little bit more on the next slide. I want to take your attention to this photo here where we have a clam, just to give you a little clam anatomy if you're not familiar. We have the mantle, that's this material here on the inside of the clam that secretes the shell. We have posterior and anterior abductor muscles here, which open and close the shell. And then we have the main body of the clam here, cut in half so that we can look inside. It resembles something like a dumpling when the clam is closed, but when we open it up to take a look, this is how it looks inside. Looking at this next slide, you can see I have a picture of each of these gonad stages, and I'll describe them for you. The first one is engorged. This would be the most reproductive stage, where we see the visceral mass here is quite large, and it's dominated by this white material that is gonad material. When a clam is ready to reproduce, its gonad enlarges and it takes over the bulk of the space inside the body. And when it's being non-reproductive, the gonad is almost non-existent. Moving to partially engorged, you can see that this visceral mass appears much smaller. Keep in mind these clams are pretty much the exact same size. It's much less plump, and it has a lot less of this white material. So when the material occupies a little less than 50% of the visceral mass, it's considered an partially engorged versus an engorged. And then we have a reduced clam. This looks altogether different. The visceral mass is very thin. It appears watery, and we don't really see any of this reproductive material anymore. Now, another way to look at this gonad stage, instead of looking at the clams themselves, because it's kind of a categorical data, frequency tables often work very well for me. So we have the frequency or the number of occurrences per treatment, and we have our different color treatments here, the cold being blue, ambient being black, and red being warm. That color should remain about the same for the rest of the presentation. And we have our different reproductive categories: engorged, partially engorged, and reduced. If we go to the left, it's highly reproductive. If we go to the right, it's low reproductive potential. And we have an NA category. This is a category filled with clams that were lost, died, or by natural causes or by predation in each experiment. So on the left, we have our first year experiment, 2021. We see in the blue, these are our cold treatments. Reproduction is high because most of the clams, about 60 out of 120, are engorged, so about 50%. Less in the partially engorged and a little bit more in the reduced. Whereas if we look at the warm treatment, if you drew an arrow, it would go from the lowest amount going engorged all the way to reduced. We had most of these clams being reduced. So we can see just by looking at this graph that reproduction was higher in the cold treatments and lower in the ambient, or lower in the warm, and the ambient in these black columns is somewhere in between. This is a system that was dominant with primary production within the water column as phytoplankton, which the clams actively feed on. In year 2022, we had greater primary production, but clams can't necessarily eat macroalgae. They're specific to the size of food that they can eat in the phytoplankton range. And we see that the cold treatment still has higher reproduction than the warm treatment, and the ambient is also somewhere in the middle, but these highs and lows are not as distinct as they were in year 1. Now, the next metric for looking at the clams is their condition, or a metric of their general health and their growth. For their condition, what we were looking at is how much of the internal volume of the shell does the clam body occupy of the available space. So this gives us, we use this equation down here on the bottom, and it gives us a number between about 1 and 100, which lets us know how healthy the clams are. A 1 would be a very unhealthy clam, and a 100 would be a very healthy clam. And for our growth, there's a couple different ways to measure the clam. Basically, what you're doing is you're looking at a stationary point on the clam that doesn't change and measuring to a point that does change. So for that, we have a height, which comes from the oldest part of the clam, or the umbo. It's the nothing changes on this side, but new rings are added at the height. We also have a length measurement, which is also from a stationary point that doesn't change to the addition of new rings as the clam grows. And we have a width, which does the same. The width can be quite important, as clams that are in higher density will often grow wider rather than longer. And when they're in lower density, they tend to grow out instead. Now, looking at that condition index in particular, we have more graphs. We have year 2021 or experiment year 1 versus year 2. And this is a density plot. If you're unfamiliar with density plots, that's okay. We have our 3 different temperature treatments denoted by color. We have our cold in blue, our ambient in black, and our red in warm. Basically, every single condition number for all of the 120 clams in the experiment falls under this line somewhere. And if you look at it, at the red line, which is the warm treatment, we can say that about half of all of the clams are greater than 60, a condition number greater than 60, and about half are a condition number less than 60. That's how you should read this graph. The y-axis is used to calculate areas under the curve, so it's not as useful if you just want to look at it. But if you want to know exactly, how many what percentage of clams fell between 40 and 60, you would use the axis to calculate that. So in year 1, 2021, we can see that the cold and the ambient lines are relatively similar, and they were actually not statistically different. But the warm line is more spaced out, showing that there was a higher amount of, showing that there was a difference really is what this tells you. And there was a statistic difference between the cold treatment and the warm treatment in 2021. For condition index in 2022, it's a little bit different. So as we see that we don't have quite the same primary production or food availability for these clams, we see that our ambient is right in the middle in this black line between the cold and the warm, where our warm treatment is geared towards a lower condition index or less healthy clams. Our cold is slightly higher, and our ambient falls right in the middle, which is something you might expect looking at a natural population. Now for our growth measurement, this measurement wasn't as strong. So we see in 2021, we had the least amount of growth clustered in our cold treatment. Our ambient was about the same as the cold, and our warm had the most growth, which would suggest an inverse relationship between reproduction and growth potentially out of this data. So the difference between the cold treatment and the warm treatment as far as the difference in height change or growth was statistically significant, but there was no statistically significant difference between the ambient of either treatment. In year 2022, we see that all 3 treatment lines are really close to each other, and they had notably less growth than year 1. And it turned out that growth was not significantly different between any of these temperature treatments or nutrient profiles. Now, in order to look at the relationships between all these metrics for the clams, I chose to use an ordered logistic regression in the mass package in R. And this type of model looks at the relationship between treatment, condition index, and growth on the likelihood of a clam belonging to one of the gonad stages. So how this impacts the reproduction of the clams. And if you are really interested in stats speak, I have a paragraph that explains it in a little less detail for understanding, but more detail for your statistician, I suppose. So looking at the results for 2021, how all these things related to each other, I just want you to focus here on the italicized words here on the bottom. So if the condition was higher, so a greater metric for health, there was a higher likelihood of a clam being more reproductive. As far as growth, where there was higher growth, there was a lower likelihood of being highly reproductive as the clams. So an inverse relationship between this reproduction and growth. And as far as how the treatments impacted things, if a clam belonged to a cold treatment, they had a greater likelihood of being more reproductive. So in these colder waters in year 1, where there was more food available, clams were more reproductive, which is the opposite of the warm treatments, where if a clam belonged to these warmer waters, they had a lower likelihood of being reproductive. Now this is water that had no bloom, so there was less food available, and clams had a poorer condition and poorer likelihood of being reproductive, which is what we might expect out of an experiment like this. Now for our model results in the year 2, 2022, condition index was still a significant predictor on gonad stage or reproductive potential, meaning greater condition index, greater reproduction, lower condition index, not as reproductive as a clam. Growth and the temperature treatment were not significant predictors in year 2, although they were in year 1. Interestingly enough, I wanted to go a little bit further and see this relationship between the reproductive stages and condition index to see if their relationships held true if we paired their reproductive category with their condition number. And as it turns out, between the categories, we have condition index here on the y-axis and our bin categories on the bottom. They were statistically different from each other. So clams that were engorged had a higher condition, partially had a statistically different condition than engorged, and reduced had a statistically different condition relationship than the other two. And this relationship held true for year 2 as well. So this was a really good metric for looking at the health and reproductive potential of these animals. Now, there was no difference between the gonad stage categories and their corresponding CI values between 2021 and 2022, with sample populations of about 360. That number gives us an idea of how robust these findings probably are. So if you look at this graph here on the right, this is another density plot where we see condition index on the bottom, the number between 1 or 0 or dead clams, or really healthy clams at 100. The blue line represents the first year, all of the condition index numbers for every single clam, regardless of treatment. They were all looked at the same time as one sample population. And year 2 in black, these were not statistically different from each other. So although in year 1 and year 2, clams were healthier in some treatments versus others, as an entire population or as an entire sample compared between the 2 years, they were not statistically different as far as their health as a whole. And this is a really good way of looking at if our different sediments had an impact on these animals. And this shows basically that it didn't. So it didn't really matter what sediment these animals came from or necessarily history of the sediment. What was more important was the amount of food that was available and the temperature that they belonged to, and the relationship between temperature and food itself. Now, as far as what conclusions can be made from this, with recruitment or the reproduction of the animals, yes, the temperature made an impact and the amount of food made an impact. The condition also held true in that respect, but our growth didn't. In year 1, we saw the opposite relationship that we might expect. When clams didn't have as much food, they actually grew. And when they had more food, they didn't really grow. They chose reproduction instead. But year 2, we didn't find any definitive answer in the data. What implications may this have when we're thinking of winter spring diatom blooms, nutrient reductions, and things like that? If we continue to see warming in the bay, we're likely to see less of these natural blooms, which will have a negative impact on this commercial and culturally relevant species. So, and with that, I'd like to leave you with my acknowledgements. Thank you guys very much for having me. It's been an absolute pleasure.
Thank you, Mike, for that presentation. And now, Wally, the floor is yours.
Great. Let's see if I can do this. Okay. Are we good? So thanks everybody for lending your ear for the next few minutes, and thanks Meredith for inviting me to do this, and thanks Candace and Mike for setting this up so beautifully. Those are really interesting and exciting talks, and I'm happy to be going after you all. So today I'm going to talk a little bit about some of the long-term work that my group has been doing in Narragansett Bay. So I started this work as a PhD student back in 2000, a fresh-faced PhD student back in 2005. And then through various funding mechanisms, in particular Rhode Island Sea Grant, we've managed to maintain long-term benthic flux nutrient and gas measurements since then at 2 stations in the Bay, Province River Estuary and Mid-Narragansett Bay. So that's what we're going to talk about primarily today. But first, I want to talk a little bit about, all of the different changes that have happened in the Bay. And so I like to think of sediments as sort of these barometers of change. They're able to integrate lots of different processes and give us sort of like a net effect of them. And so that's what I'll show you today. But first, I think that it's really important as we think about how to understand an ecosystem and how to manage an ecosystem to remember that it is not alone in the world, right? It is set into this stage. So in Narragansett Bay, for example, right, like any estuary, it's set amongst this huge stage of a world that is really complex and changing and quite dynamic. And so when we think about whether or not we should increase or decrease nitrogen or how we want to manage a system, we need to also think about the many different complex changes that are happening around that, which will ultimately impact the results of whatever management interventions that we make. So I'm just going to highlight a couple of these, and I've talked about this before, so I'm sorry if I am beating a dead horse here, but I really think this is quite important. So if we think about all of the different changes that Narragansett Bay, like many temperate estuaries, are experiencing, it's getting both wetter and stormier. So the average rainfall has increased somewhere between 0.4 and 0.7 inches per year since the late 1800s. And that means that we're actually increasing freshwater input, although it's still relatively small compared to other estuaries, but we're increasing freshwater inputs into Narragansett Bay. And the amounts of sort of intense storms are increasing, and they will continue to increase through future climate change. So we're changing sort of both the amount of precipitation that's coming and then the intensity and timing of it. We're also, of course, warming Narragansett Bay. So both the air and water temperatures are increasing. You can see this in sort of the air temperature here. We've got sort of a longer period from 1949 to 2015 in black, or in red here, you can see a change from 1960 to 2015. Whatever line you use, you can see that the air temperature is increasing somewhere between 1.3 and 1.7 degrees across the watershed. The reason that matters is because it means that there are metabolic processes within the watershed that will be changing, and those metabolic processes, like the bacterial transformation or decomposition of organic matter and nitrogen, that's going to be probably increasing with this temperature increase. So changing across the watershed, which means potentially that the amount of nutrients and carbon coming in can also be changing. Within the estuary itself, we have a whole variety of records, whether it's the long-term phytoplankton, long-term phytoplankton data set from mid-Narragansett Bay, or the trawl data, or NOAA buoys, which the NOAA buoy is shown here in gray. You can see that surface water temperatures have also been increasing. That shouldn't be a 7, that should be a C. So all the way up to about 1.6 degrees Celsius over our period of record. And as we increase the warming water, then that means we're also going to change a whole bunch of different processes within the water column, whether that is the timing of zooplankton, the grazing of bacteria and zooplankton, the timing of different larvae blooms, et cetera, all will be changing because of this increase in temperature. Temperature can also do things like increase the stratification of the water column. So when you warm a water column, and you can get like a more buoyant layer on top, and then you can keep the cold water on the bottom, which means that migration, or it's kind of funny to think of phytoplankton migrating, but they do go up and down to get light and nutrients. You can think that that can change because of stratification in the water column. Additionally, warmer water holds less oxygen. So we can imagine that over time, as you start to warm the water column, you hold less oxygen. And that is in fact one of the major drivers of low oxygen conditions globally. It's also important for coastal ecosystems. There are also other changes that have been found, like over time, there's been an increase in the number of cloudy days, and there are really important connections between when phytoplankton bloom and how much they bloom, how much growth they exhibit, depending on the timing of light. So you can imagine if there's more cloudy days, we may sort of push or lose winter spring blooms or change the timing of those things. All in all, it seems that sort of one of the major things that we can think about for Narragansett Bay is the one constant is actually change. And I can't remember exactly when, but I remember Candace at one point said that she's never really seen a normal year for Narragansett Bay. And I think that that's likely true for most estuaries, right? It's just that are very dynamic with lots of different things happening. And so when we begin to think about sort of how we might predict or understand these systems, it's important to keep all of these changes in mind. So let's just sort of recap this. When we're looking at these systems, and if we're trying to understand the major changes that are happening, we are going to we can list all of them, right? So I'm going to go and I'm like study sediments because I want to try to understand this, but how do I even keep track of these things? So let's just do a quick recap for what we've seen in Narragansett Bay. Over the last 40, 50, 100 years, we've seen an increase in precipitation, increases in air and water temperature, increases in cloudy days, decreases in wind speed, potentially decreases in light, shifting North Atlantic oscillation, which is a large-scale atmospheric process, decreases in phosphorus inputs from land, like Candace has mentioned, and of course, these decreases in nitrogen inputs from land, which started, as Candace noted, in 2005, and then really increased in 2012. I really want to highlight that point, though. These changes in nitrogen coming to Narragansett Bay are a relatively recent phenomenon. These other changes that have been happening in Narragansett Bay have been happening for decades. And so when we look to see the long-term changes in the system, it is not only nitrogen that is changing, but it is all these other large-scale sort of regional global forcings. One of the things that we spend an enormous amount of time doing in my lab is collecting mud. We use sediments as barometers of change because they can integrate all of these different processes and give us sort of this net effect. On the one hand, that can be helpful because we can sort of, come out with like a net effect. But the challenge, of course, becomes we can't always, or rarely, I should say, we can rarely say, this net effect is because of X, Y, and Z, right? It sort of homogenizes all of the different changes. So why we use sediments and why they're such a great integrator is because there's this tight relationship between the sediments, so shown down here in brown, and the water column. And that relationship is called benthic pelagic coupling. Benthos or benthic being the bottom and pelagic or pelagos being the water column. So you can imagine that as phytoplankton bloom in the waters, here's a collection of diatoms. They're using up the nutrients. When they fall and when they die and fall to the bottom, they get decomposed in the sediments. And then these bacterial processes break down organic matter and use up oxygen and can release dissolved inorganic nitrogen and other nutrients like phosphorus and silica. The strength of this relationship between the water column and the benthos is typically quite strong in coastal systems because of their shallow nature. So if you think about like a transect going from the coast out to the continental shelf and beyond, you can imagine that it's this relationship between the water column and the sediments are quite tight in coastal systems, and then they expand outwards. So we would expect a tightness here. Essentially, this organic matter falls, fuels this bacterial decomposition, and then these nutrients get recycled out of the sediments and back into the water column to fuel future phytoplankton blooms. This dying organic matter on the bottom can also fuel a process called denitrification, which is sort of this important process. It's a natural filtering process that can remove a good deal of anthropogenic nitrogen or human-derived nitrogen that comes into coastal systems. And so what it does is it takes this biologically usable form of nitrogen, let's say nitrate, and convert it into dinitrogen or N2 gas. Once it's converted into N2 gas, we consider it to be basically like removed from the system. It's back in, we're bathed in N2, our atmosphere is about 80% N2. So when you take it out of this dissolved inorganic usable nitrogen form and put it into gas, most organisms on Earth cannot use it. So this is good because we consider it a good process because as we sort of dump all this nitrogen into coastal systems, here is this natural filtering process that can help remove it. Of course, because bacteria are amazing, there are a group of bacteria that can tap into this dissolved N2, into this dissolved gas, and turn it into a usable form of nitrogen. And these are called nitrogen fixers or diazotrophs, and they can fix this nitrogen, turning it into a usable form, ammonia, that other organisms can also use. So first, we're going to sort of talk about this decomposition process of sort of aerobic decomposition, and then we'll talk about this anaerobic process that removes nitrogen. So one of the things that got me sort of interested in this process long ago was this phytoplankton record. This is one of the longest, if not the longest, phytoplankton long-term record in a water column in an estuary anywhere globally. And it's thoughtfully maintained still by the Graduate School of Oceanography and Tatjana Reinerson's lab. So thank you to them for keeping this going. And I just want to highlight that this is measuring water column production using chlorophyll A. Can be a proxy for production, trying to understand the phytoplankton, how many phytoplankton are around in the water column. And this is taken right around that mid-bay site that both Mike and Candace mentioned, and I'll show you again in a second. And so what you can see is that over this period of record, there has been a long general decline in the amount of chlorophyll in this mid-bay site. This sort of started in I would say the 80s and 90s and continued throughout the 2000s. Certainly there are times when there are other sort of blooms that happen that are falling off this record, as any natural record we would expect to see. And even in the last few years, there's been seems to be a little bit more of a phytoplankton here, but still in general, we see this nice general decline and a nice clear decline, and it's a significant decline over this period of time. These two arrows here are highlighting the time when we started to decrease nitrogen in 2005 in the Bay, and then really got good at it in 2015. And as Candace pointed out, we're still doing that up to 60%. I want to highlight this again to say that you can see that there was a decline in this chlorophyll record long before we started to take out the nitrogen. And so by taking out the nitrogen, right, we were likely going to even add, as Candace showed, we were adding even sort of more of a decline to this. But I have a hard time getting behind thinking that the nitrogen reduction, right, is causing this decrease, because we hadn't done the nitrogen reduction yet. When we are starting to change the amount of water column production or chlorophyll here in the water column, that means that the amount of organic matter that can fall to the bottom and fuel those sediment decomposition processes is also going to decrease. So essentially, you can think of it like the food that's going to fuel the microbes in the sediments is going to be, there's going to be less of it. Additionally, you might remember that I mentioned that the water is also getting warmer. And in a warming water scenario, then we can anticipate, and there's been quite a few experimental work and modeling work that has shown that you can increase bacterial decomposition in the water column, so that not only is the amount of organic matter that's reaching the bottom lower, but also sort of the quality of that organic matter, it can also be less. Additionally, when we start to see this decline, we can imagine then that tight benthic pelagic coupling, that tight relationship between the water column and the sediments over this time period may in fact be separating, because if we have less organic matter coming down, then we have less decomposition, and then we would have less sort of recycling of those nutrients to fuel future phytoplankton. It's not just that the chlorophyll here is declining at this mid-bay site, but we also see changes in the timing of that bloom. So historically, there was a sort of dominant winter spring bloom that kind of characterized Narragansett Bay. In the beginning, I would say somewhere in the 1970s, we see that kind of disappears, and we have a much more sporadic time. So what we're looking at here is this is the month of the year, and then over the time period of record, and we're just finding when the maximum bloom occurred, just putting a dot there. So you can see that it's quite sporadic, and then these red here are sort of just highlighting the most recent after the major nitrogen mitigation efforts in the Bay. Actually, and the more I stare at this plot, the more I think like maybe these were the weird years, and this is actually how the Bay functions. I'm not sure, but there's clearly here we're not sort of settling on a single time of year for a maximum bloom. Okay. So how do we sort of try to understand this? So like I said, we've been going to 2 stations in Narragansett Bay since 2005. We try to go at least once a summer. Some years, depending on funding, we've been able to capture winter months. And as of the last few years, we've been able to do multiple times a summer, or a little bit in the fall. So we get at least once a year since 2005 at the Mid-Bay Station, and almost at least once a year at the Providence River Station up here. These stars are obviously really, really big. We go collect cores with divers here at this site and use something called a pull or a push core here off the boat here in the Providence River site. This is kind of like right off the Save, pretty close to the Save the Bay dock. And this is that close to the long-term station that everyone's been using in Narragansett Bay for a long time. It must just have a big divot of sediment out of it. Okay. So we collect these sediment cores. I'm always happy with the core. We take a lot of pains to bring back these intact cores that maintain the vertical architecture of the sediment, because we want to make sure that the microbes and the organic matter are like happy and as relatively undisturbed as possible, given the caveat that we are taking a core and pulling it out of the ocean. And we drive these back up to BU, and then we can incubate them in an environmental chamber and in the water bath in these gas tight sediment core system. And I can talk all about those details if you're interested. So let's just take a look here to see sort of how things have been changing and what they look like. So here in the gray dots here, I'm showing you the amount of oxygen, ammonium, dissolved inorganic phosphorus, or silica that is fluxing across the sediment water interface. So if you see an increase in ammonium or phosphorus or silica, that means it's coming out of the sediment. And if you see an uptake, that means it's going into the sediment. Oxygen, I think I'm going to show you in like 2 different ways here, which is totally confusing, but just think of this as like sediment oxygen demand. So essentially, this is actually consumption of oxygen by the sediment. Sometimes it's shown negative, sometimes positive. Here I'm showing it to you positive. This is a classic sort of response that we would anticipate seeing from sediments over a temperature range. So essentially, you can hopefully see that in most of these cases, there's a fairly clear pattern that as you ramp up the temperature, you see an increase in the flux of whatever you're looking at. So an increase in the oxygen demand from the sediment, an increase of ammonium coming off the sediment, an increase in phosphorus, and an increase in silica. And these are data from the 1970s and 80s collected from like Candace Oviatt and Scott Nixon and Mike Poulsen and Barb Nowicki, and I'm going to miss people, so I'll stop saying them, but a whole host of work here. The purple shown here are showing you the most recent data between 2005 and 2019. We did not collect in 2020 because of COVID, and I wasn't allowed to cross state lines, but we do have data from 2021 and 2022. For clearness, have just stopped it here at 2019. So that, and I'm behind on the 2022 data. Okay, so what I want to show you here is that in all of these cases, except for silica, we see this sort of a different response, and that is that we don't have as high rates as we would have anticipated or as we had in the past. And in fact, when you do the comparison, there is a 40% decrease in sediment oxygen demand over this time period, and almost an 80% decrease in phosphorus, about a 50% decrease in ammonium flux, and no change in silica. And this is consistent with what I found in the early 2000s. And all of this is actually consistent with what we found in the early 2000s. So essentially what it's sort of pointing to is that these microbial decomposition processes in the sediments are dampened, and they are likely dampened because there's not enough organic matter, like they're not getting fresh organic matter or fresh food to eat during the summer months, or during, the idea being that it would bloom in the winter and then fall to the bottom and kind of sit there. And as the system warmed up, then the microbes would become active and chew up those that fresh organic matter. But regardless of the reason, we can see that these fluxes are still dampened in their response to temperature. Just to get you sort of oriented here, this is looking at sediment oxygen demand again. The colors correspond to the different times of the year. So the winter is blue, and the green is spring, and the red is summer, and the like a brownie color is fall. So you can see most of our data collection occurs in the summer and fall. Starting in 2005, and you can see this is Providence River site, so up near the Save the Bay, and this is that mid-bay site. The sediment oxygen demand in the Providence River is still significantly higher than that in the mid-bay. And there's no really clear trend over time here when we look at it this way, to say like, oh, there's a steady decline. But we can see certainly hit a lower period here in the early or mid 2000s, and then things popped up a little bit again. And certainly down here in the mid-bay, they seem to be declining again, and potentially here in the Providence River estuary. Okay, so I can take these numbers and I can use a relationship developed by Scott Nixon to sort of examine, give another estimate to primary production. And I wanted to do this because every time I see Candace's numbers of primary production, I want to see if this method works. So if we were oceanographers, we might use something like a sediment trap, and that would allow us to sort of gather all the organic matter that was coming down from the water column and capture it on the sediments. And then we would know the actual loading of organic matter to the sediments. In shallow systems, that doesn't work for a lot of reasons, like there's resuspension of material, there's more organisms that can get in there and like into your trap and chew up your organic matter, so it's a complicated measurement. So instead, we can use this relationship that's looking at primary production plus organic matter inputs, and it's related to this benthic remineralization. So that's just this idea of like the decomposition of organic matter. In Narragansett Bay, there's very little organic inputs coming in from land, and so we can kind of like ignore that number, and basically we can use our decomposition that we're measuring in the sediments to sort of predict or estimate the amount of primary production that's coming in. And so just when I do that, I can compare that to some of the measurements that were made previously. And in the 1970s, and I think Candace had put this too as her earlier numbers, we had rates of around 300 grams of carbon per meter squared per year in the bay. And if I take the time period of decomposition that we've been measuring between 2005 and 2019 and plug it into that really in the linear regression, I get an estimate of around 170 grams of carbon per meter squared per year, which I think is really quite close to Candace's sort of more integrated measurements all over the water column measurements all over the bay, around 200. And my argument would be that it's not just nitrogen management sort of decrease in the productivity of the bay, but also these climate impacts that I talked about previously. Okay, quickly, I just want to touch on the idea of this nitrogen removal process that I mentioned, denitrification. So when we bring those cores back to the lab and incubate them, we collect gas samples to measure the flux of N2 across the sediment water interface. And we use a membrane inlet mass spec, and this is that setup with its appropriate GIFs so that the mass spec behaves happily. And we can measure the flux of N2 across the sediment water interface. So it's a measurement of sort of like a net flux, because both of these processes can happen in sediments. So I'll show you this here. So every time you see a positive number, it means it's net denitrification, so net removal. And every time you see a negative number, it means that it's net N2 uptake or indicative of nitrogen fixation in the sediments. Again, this is the Providence River estuary site, and this is the Mid-Bay site. This is a really fun long-term record. There's not that many long-term benthic flux measurements that go on this long. We're almost, we're creeping up on 17, 18 years here. And there's only one other one that I know that is longer than that. So that's very exciting. But what you can see is that the process of either denitrification or N-fixation is quite dynamic in the bay. For a small period of time, the Providence River and Mid-Bay sites were significantly different when I last looked at this in 2014. But now, putting all those data together, these two sites are not significantly different, likely because of the high variability of them. And you can see, and I think this is a really important point I want to make, is that sometimes the system can net nitrogen fix, and sometimes it can net denitrify, and sometimes it doesn't know what it's doing. And I think this is really important because denitrification is a key component in nitrogen budgets, and we often measure it once and we're like, okay, we're all done. And what these data really help show is that this is a super dynamic process that's changing quite rapidly over time, and in order to get both time and location. And so in order to really understand this number for a nitrogen budget, we need to have sort of many more measurements in lots of different systems than we currently do. I can go ahead and just look at these in a little bit more detail. So the average net N2 flux for these two sites is somewhere between around 30 at the Mid-Bay station and 56 or around 60, let's say, in the Providence River estuary. That's taking all of the fluxes, regardless of positive or negative, so just the net N2 flux. So overall, it's indicative of net denitrification, which is consistent with the long-term patterns in the bay. However, these are still 70% lower than what was measured in the 1970s and 80s. So these rates of nitrogen removal are substantially less than what we saw in the 70s and 80s. If we look at just net nitrogen fixation numbers, they account for about 15% of the measurements that we make, and they range somewhere between 80 and 100, depending on where you are. So an N fixation rate in the sediment, somewhere between 80 and 100 micromoles per meter squared per hour. And then finally, if we look at just the net denitrification rates, where we see that Providence River looks a lot higher, about 120 almost micromoles per meter squared per hour, where Mid-Bay is more around 70. I'm not highlighting here any of the net zero measurements, but it is not uncommon to measure a net zero, which simply means that the processes of N-fixation and denitrification were likely both co-occurring in sediments and essentially give us a net zero. So you're not removing nitrogen nor adding it to the system. I'm a little bit worried about time, but I just want to highlight a couple. Oh, why is it doing that? Oh, okay. Well, it wants me to go faster. Just want to highlight one fun thing that I have been able to work on with Chris Kincaid over the last few years and a host of others. So one of the things that we're trying to understand is how the nitrogen budget looks for Narragansett Bay and how it's been changing. So we know that there was lots of nitrogen coming into the bay for a very long period of time, since the late 1800s until around the mid 2000s, where we began to dial it back. And then in 2012, really dialed it back. And so and then we know, right, that like denitrification, which is this major nitrogen removal process, is also quite dynamic in the bay. And then there's this other idea that this sort of fundamentally built into what an estuary is, right? So if an estuary is like where freshwater and saltwater meet, we've been spending a lot of time thinking about this freshwater inputs of nitrogen, but there's also, of course, the oceanic inputs that could potentially bring nitrogen into the bay. And so Chris is leading this effort, and he wanted me to make sure that I mentioned that it was inspired by a conversation he had with Scott Nixon. And actually the first project that I worked on when I joined Scott's lab was this project. I was measuring nitrogen, collecting a lot of Niskin bottles and measuring nitrogen in the deep water. But what we're looking at here is trying to understand how much nitrogen really is coming from these oceanic bottom sources, basically like off the continental shelf and then up and into Narragansett Bay. And if that map would let me show you that map, it would just show you that there are like pathways of water into Narragansett Bay. And one of the big pathways is really up the East Passage. And at different times of the year, there are these intrusions, right? Which literally there's this deep bottom water coming off the shelf and up into Narragansett Bay with fairly high amounts of nitrogen. And there's this like, I can sort of get you in here, can like really show you this amount of nitrogen or water really moving in. And it's a lot, it's a rate of water input into the bay that's on par or higher than what we're seeing from rivers. So just quickly, what this diagram is showing you is sort of different ways to imagine how much nitrogen is coming in from that oceanic source. So these are the wastewater treatment inputs, that and millions of moles of dissolved organic nitrogen. And here's the river amount. And then depending on like what number of nitrogen we use, if we use like the lowest nitrogen value we have, or sort of the average or the max, you can see that there's quite a range that we're still trying to refine. But you can see that it's potentially quite an important source of nitrogen that's coming into Narragansett Bay. And we have yet to truly understand what that is going to mean for productivity in the bay and for the nitrogen budget. I also just want to highlight here that Sawyer Ballant and Autumn Oskowski have been working on, and Meredith Hastings have been doing some neat work on atmospheric deposition and the potential there for an increased amount of some nitrogen coming in from the bay there. And I just read that paper, it came out this year, and it's another potential source of nitrogen that we've likely underestimated into the bay. So with that, I'm going to stop. I want to thank so many people for talking to me about Narragansett Bay, my funders, and you all for lending an ear. And you can find us at fowellerlab.com or on Twitter. You can always email me. I'm always happy to talk about Narragansett Bay. And with that, I will stop. Thank you so much.
Well, thank you so much to our speakers for contributing. I just wanted to actually suggest there's some people have left questions in the chat. So feel free to do that. Also feel free to raise your hand if you'd like to speak for yourself. So just to kind of get this started, I'll start with the questions raised in the chat about, and Candace, this refers, I think, to your suggestion of maybe kind of helping that nutrient input maybe in the winter to help with that, that winter spring bloom. And so the question is, how can the pulse of phytoplankton in March enhance clam recruitment if clams aren't feeding until May when temperatures are above 10 degrees Celsius? And I'll tag on to that question in terms of what I was thinking in terms of timing of a release of nutrients and also the intensity, if you have any sense of how much do we release. So.
Yeah. Oh, thank you, Meredith. I'm happy to give a try at that. The pulse of organic matter that goes to the bottom in the winter spring bloom, it doesn't decay immediately. It's cold, and it settles to the bottom, but it's resuspended depending on storms and tidal currents. And as it's resuspended, it is eaten by clams as the waters warm up in the spring. So it's like a refrigerator storing food until the clam is ready to eat. And that I believe is how it works. I think there is some bacterial utilization of the organic matter that goes on year round, even in the colder months. But the clams, it's correct, do not start to feed in the very coldest part of the year. They wait until the water column warms up to some extent. But that fresh organic matter is still fresh at that point. And to some extent, it's resuspended and re-available to them with currents in the bay and storms in the bay.
So would you suggest like a certain timing? Like, would you, in terms of the situation with storms, you know, as Wally, you've described how in recent years and what you mentioned, Candace, with the flushing rates increasing with storms. So I guess I'm imagining you working with the folks at the wastewater facilities to be like, all right, when exactly do we do this? If we were.
Sorry, I didn't quite understand. You want to know the timing of?
Yeah, like I guess it's like, you know, would you have to work with our folks at the wastewater treatment facilities?
Oh, in terms of releasing nutrients?
Yeah, yes.
Yeah, it's fine to release it all the way up till the first week in April, I would say, or just to be on the safe side, you might say to April. So probably November through April, it would be fine to release nutrients. Yeah. Yeah.
Okay, I think this next question kind of came around during the time, Wally, when you were talking about how all the different changes have been happening in the Bay over this longer time period. And it's just a straight, are we headed for a Bay die-off?
That is very pessimistic. No, I don't think that we're headed for a Bay die-off. I think that ecosystems are resilient and interesting. And I think that Narragansett Bay is experiencing lots of changes. It has been for decades, for all of the decades that we all collectively have been looking at it, right? And so I think that no, things are changing, of course, but not a die-off. No.
And the next question it's more technical, as you can see from the chat.
Yeah.
And the question refers to, you know, whether you checked fitting an exponential regression for the historic chlorophyll versus year graph versus linear, because it might look like that an exponential logarithmic decay is approaching an asymptote.
Yes, so we every time I've made that plot, I've used exponential. And last night when I made that plot, the linear regression was a better fit, and so I went with it. It's not that much better, but it is slightly better. So linear regressions are always easier to work with. So I just I use the linear regression. But yeah, typically we've done exponential, but it's currently a better fit to use linear.
And then the other question is about how much does the North Atlantic Oscillation play into the nutrient budget for the Bay? Does it drive the offshore intrusion? I guess, you know, like Chris Kincaid's work has been showing from Rhode Island Sound.
Candace is more of an NAO person than I am, and I'm going to get flashbacks to comps when Candace asked me about the NAO, and I literally like panicked and forgot all of it. So Candace, do you want to take that, or are you going to throw me back in the hot seat?
I think it's your question, Wally. I don't have good measures of what's coming in the East Passage from offshore yet, so I'm kind of adrift there, and the pattern of it I have no understanding of. So
yeah, so we have not looked to see any connection with the NAO. And also Dave Borkman did a lot of that work too, I think, if I'm remembering correctly. So Chris and I, and to my knowledge, he hasn't done that look either. But the intrusions do seem to set up tidally, and they do seem to be particularly strong in the summer. So it would be interesting to sort of make that next connection to larger atmospheric patterns. But I feel like at this point, we're still very much in the stage of trying to understand when the intrusions happen, exactly where they're happening. And Chris did ask me to mention there are ADCPs that could be deployed. So, you know, if there is funding, willing people, we can do that.
I have a question, and I think this maybe Mike can answer this about do we say mesocosm or mesocosm? I'm still not sure how we say that word, but I'm going to go with mesocosm. What kind of limitations did you guys find with working? I guess the pros and cons. You already talked about a little bit about the pros where you can have kind of a controlled environment to work with, but are there any limitations that, you know, things you wish you had, or things would you wish you can continue using those types of experiments? I guess how helpful really was that, if that makes sense?
The utility of a mesocosm is that it can be changed to fit different experiments. So it being modular is the strongest facet of a system like that. Limitations to certain experiments are based on, you know, how large your system is and what exactly you're trying to do. So the older Merle mesocosms were larger. You could get a deeper water column, and you can get a beneath the photic layer. So you could have an area where light is not reaching and see exactly what's happening with phytoplankton in the surface and things like benthic pelagic coupling. That's something that we didn't have in our 2 years of experiments because we had shallow water mesocosms. It's not necessarily a pro or a con. It's just based on, does it suit the experiment you're designing them for, and can you make it modular enough that it can? So I think that's an answer. Yes, it's the utility is that it's changeable, but you should look at it as a whole and say, is its size relevant to your experiment? Is the depth, the amount of water, that kind of thing? And can you change things like the mixing and the amount of water coming in and the threshold for how much you can adjust the temperature and things like that? So there are limitations. They are, it's an artificial environment. So it's good at looking at relationships and separating them from other relationships and looking at more not superficially, but more simplistically than an environment that's open and mixing. But it can definitely give you an idea of how things are impacting things like temperature and water additions. And, it depends on what you're looking for, what you're looking at.
Great, thank you. We have another question about rectifying the decline in clam production with the excellent growth of oysters down bay in Dutch Harbor. So historically, oyster leases were north of the bridges, but we see a strong strong growth south of the bridges, despite the fact that oysters are generally more adapted to more highly eutrophic waters. So, I mean, again, that was kind of what I was thinking too, not specifically is that, but causation versus correlation. And that's just a really specific question related to that. I don't know if anyone would like to.
Well, I find Mike is a little bit silent, so I'll try. It is true the aquaculture people are finding good growth in the oysters at the aquaculture farms in the bay, particularly in the lower bay. They're doing just fine. And part of the reason probably is that the lower bay has not changed as much as the upper bay with the nutrient drawdown. The gradient has been reduced mainly by lowering nutrients in the upper bay. So the lower bay has lower nutrients than it did have, but proportionally less. And the other thing is the oysters are very much subsidized by the currents. So there's pretty good, strong currents in the lower bay, which continually moves organic matter past the oyster. So they're eating more phytoplankton than the area just in the water column above them. They're subsidized by a much larger area. So I would expect their growth to be unchanged. And as I understand it, they're still growing quite well. And Mike, if you want to add to that, go right ahead.
That was great. Thank you, Candace.
All right. Chris, I think if you want to go ahead and unmute yourself to ask your question, you should be able to do so.
Okay, hi. Very interesting information. Good to see you, all of you, Ollie, Mike, and Candace. I do have a question related to some of the information Mike presented. I found it really interesting that even when you were adding nutrients to your mesocosm studies, you were not seeing phytoplankton blooms because the macroalgae were basically grabbing those nutrients, as I understand your results. So one of the questions I have is, do you have any indication with other systems such as Tampa Bay, Boston Harbor, Sarasota Bay, they've seen a sort of a tipping point where as the nutrients would decrease, they decreased their nutrients from sewage treatment plants by 100%. They removed completely all of the wastewater treatment nutrient addition. And what they saw is over about a 10-year period, there was a shift. Actually, there was almost an immediate shift from phytoplankton towards macroalgae, and a shift towards the macroalgae as being the primary producers. And then over about 10 years, you got to seagrasses starting to grow. And have you looked at Narragansett Bay? I live near Mount View, just north of Quonset, and I've been taking pictures of the shoreline, and I've been noticing what I think is a shift over, almost like a tipping point, to macroalgae. I see much more macroalgae now along the shore, and everyone, as Candace mentioned, is noticing a clearer water, a lower turbidity to the water due to phytoplankton blooms. So how much, along with all of those other complex issues you guys are looking at, like temperature shifts and increases in rain, how much of our changes is due to macroalgae now increasing and potentially going towards a seagrass, although unfortunately there's no seagrass in the north. So I think it's going to be a very slow change for Narragansett Bay unless we did some kind of planting of seagrasses. I know they're doing well in prudence. But anyway, my question is, are we seeing a tipping point shift in primary production in Narragansett Bay?
Well, I can see that Mike's hesitating there, so I'll try again. Yeah, I think with the clearer water that there can be an increase in the benthic macroalgae growing in the coastal area. And I think it could be quite significant. And I'm not surprised that that's happening in some areas. I do wonder whether the overall I've been trying to get some data to figure out if the overall macroalgae is increased or decreased with the nutrient drawdown. I'm very interested in that data, and so far I haven't uncovered any. I'm looking for it. And I do think that now that light can reach the bottom in most areas of the bay, that we ought to be doing some experiments to figure out how to restore eelgrass to the bay. I think the water column is ready to receive those kinds of plants. The temperature is not, and that's the problem we have to overcome. But I think those experiments should be done to figure out how to restore eelgrass to the bay. Good question, Chris.
If I can pile on to that. So the macroalgae story is one that is also of great interest. There was some work by the Narragansett Bay Estuarine Program to go after some of the fisherman knowledge in the bay to see how the bay has been changing. And a lot of the fishermen in the bay and aquaculturists have been noting that there are sort of big changes, they think, in the amount of macroalgae that's happening. They like the weed, they keep talking about the weed in the bay. So we're trying to figure out a way to start sampling some of that. So Candace, we should talk because there does seem to be an increase in that. The other thing I think that it would be important to start to look at are microphytobenthos. So the sort of phytoplankton that oddly don't live in the water column, but like to live on the surface of sediments. And they do super well even under low light, and they can take up lots of nutrients. They totally change nutrient dynamics, and they can be quite productive, and they can be a really big source of food for organisms, in the sediment. And if we're really clarifying that water column, like it seems we are, then I suspect we'll also see that. And then just, yes, a plug, mesocosm work, seagrasses, genetic species that handle higher temperatures like those from Virginia.
It seems like Bob, I don't know if you feel like your question about when we could expect eelgrass to recover with greater light penetration has been answered. But like when you talked about the turbidity being reduced, but then on one hand, Wally, you were saying how they're cloudier days.
I think the larger thing is what Candace just pointed out, the temperature issue. So we're doing we're doing one thing, like we're increasing the clarity of the water. That's a bonus, right, for a group of organisms. But at the same time, we're like ramping up the temperature, and seagrasses really don't like that. So I think that, and then we've decreased the nutrients, so that would be good. They would be happier with less nutrients. But the temperature thing is going to be, I think, a really big challenge. And so unless we get kind of bold and experimental there, I think it will be hard to bring back the current Zostera genetic stock to Narragansett Bay.
I wanted to ask how much zooplankton and grazers play a role in the primary production, how that's integrated into this. Because I know there's a lot of talk that there's a direct link between the phytoplankton and then the fish, but like there's a lot of the middlemen, if you will, or the middle players. And so I've had conversations on the side where there's like maybe a greater role that grazers might be playing. So I was just curious what in your work, where you see that kind of falling in line with this.
I'll go first on this, and perhaps the other two would like to jump in. One of the reasons we see a spring diatom bloom in the coldest portion of the year is because there's a lack of zooplankton grazing and benthic grazing. So the fact that nobody is eating that phytoplankton allows it to increase, even though growth is somewhat slower in colder months of the year. So zooplankton have a huge impact. And about April, it gets warm enough for zooplankton feed, just as it does for clams to feed. So they become quite abundant in the water column and chlorophyll plummets. You saw that inverse relationship between chlorophyll in the water column and temperature. And part of that is due to grazing by zooplankton in the water column, and to a lesser extent by filter feeders sitting on the bottom. So grazing is very important in terms of controlling biomass of phytoplankton in the water column. And through the summertime months, low chlorophyll is generally indicative of high grazing rates.
And I would say fish as general are, many species have a zooplankton stage. So when these blooms are high, early in spring, these early zooplankton from these different species are then able to get a jump up by, eating that phytoplankton down once the temperatures increase and they're active. So they're important for controlling that phytoplankton bloom, but the bloom occurring is also important for them because that's how it supports the fish as they enter larger trophic levels, becoming bigger and more commercially available.
I'll ask another question regarding like timeline. So Wally, you were kind of really talking about how over decades we've had these long-term changes, and then really only recently we've seen the nitrogen reduction. I guess the long-term changes, has that pace allowed for adaptation, you think, better? Like, I guess my question is, like, has our nitrogen reduction been so drastic in a really short time frame that adaptation for different life cycles and things, I guess I don't know how to articulate this well, but like, what's the timeline difference of change that we can anticipate or see?
Yeah, that's a really interesting question, and I don't know if I can answer that. So I think one of the key things to think about is that I suspect that we are like just at the edge of seeing the changes that the nitrogen reduction is showing us, and that what we're seeing here are, we've had these long-term sort of regional climate and larger scale changes on top, and now we've applied this nitrogen change, and so that's going to push it in a direction too. And then I suspect that as we keep going, we're going to see more drastic changes because of the nitrogen mitigation. And I think it's a really big challenge to imagine how things are evolving and changing. I don't know, Candace, maybe and Mike have an idea on this, but I think that, I don't know if we can, I don't know if I think what you're asking is like, are they set up because they've already seen so much change to like also deal with this change? Or is this change so drastic compared to those longer changes that it's like too much?
Yeah, it's more of like, is this change so abrupt and so fast when you think of like timelines and how like climate change, like people will be like, climate change is natural. Like, yes, but also, yeah.
Yeah, I don't know. I mean, for me, I feel like many estuarine species are very used to like experiencing lots of changes. Just if you think about like what happens on a daily cycle in an estuary, like pH swings, it can be like 1 pH unit, and they can, right, and like water temperatures can change rapidly, and then the big intense seasonal cycles that estuaries experience. I feel like they're adapted to lots of changes. So I'm not sure. But I don't think it's like I don't think it's like a shock to the system. I don't think it's like that. But I think I don't think it's like that because the life cycles are off a little bit on that. Candace probably and Mike have ideas.
I kind of look at the large scale changes. It's not so much a change to the system, like it's going to be drastically or devastated. It's a change to us as humans and our understanding of the system. We're living in some of the, our coastline, it has some of the fastest warming waters on the planet due to climate change. And we see cold water species moving northward and warm water species also moving northward. So we have more, species that the environment is changing for. So we have invasive species coming up to us, and we have our species leaving. You can see that in kind of the lobsters, and how lobsters left the bay and how they're having no problem in Nova Scotia and Maine, but we don't have much of a lobster fishery here anymore. So it's, to me, it's a change to us. And that's human beings kind of resist change a little bit when it comes to looking at things as a whole. We like generalizations, but I think the Bay will be fine. The Bay will just be different in my lifetime, probably.
There's another great question actually that I was also thinking. It's so far the focus has been on clams and maybe to a lesser extent squid, the example, Candace, that you brought up. What about other populations and species of other species? I was actually thinking like maybe groundfish or demersal. I'm thinking like sea robin. That might be more, I guess, as a species with that benthic pelagic coupling. So I guess, and that kind of goes into like, are these part of like next research questions or things to consider? But we'll start with like, what other species?
Okay, yes. I can't remember with sea robins. I think the striped sea robin likes colder temperature, or I can't remember which one is more boreal, the striped one or the common sea robin. But one that likes it warmer is doing okay, and the other one is not, I think. Somebody probably in the audience knows a lot more about it than I do. But I could say that we tried very hard to look to see if fish had, as biomass as a whole, had been reduced as a consequence of the nutrient reduction in the Bay. And I used the Rhode Island DEM trawl series in the Bay, and I also used the GSO trawl series in the Bay. And it's very complicated to figure it out because we had a huge pulse of increase of crabs and lobsters in the late 1900s, and then a decrease in the early 2000s of decapods. That was a very large biomass change. And then imposed on that from 2005 on was the nutrient reduction. So I looked at it rather late in the period of the nutrient reduction to see before the final nutrient reduction and after the nutrient reduction to see if there had been a change in total fish biomass from those two different trawl surveys in the Bay and several different species in several different stations in the Bay. And the Upper Bay had actually increased somewhat in species of fish and biomass of fish, probably because low oxygen conditions have improved up there. The Lower Bay stations, actually Warwick, Neck, south to GSO and Gould Island and East Passage have actually lost biomass of fish. Not very much, considering the high variability of fish from one year to the next. It's on the order of 10%. So there may have been a reduction correlated with the nutrient decrease of around 10%. That was a statistically significant amount of change because of the large data set we had. But given the high variability of fish in the Bay, I really don't put much emphasis on it. I wouldn't be willing to say that fish have actually significantly decreased in the Bay. But there is a trend of Lower Bay stations having fewer fish and Upper Bay stations having more fish, which is not all bad.
Would you consider Narragansett Bay to be oligotrophic? Is that a word that we could use to describe the Bay?
You could say it's
Yeah.
undergoing oligotrophication. Right? Like it's undergoing a process that's leading, or processes that are leading to lower primary production.
And
I would agree with Wally. Yes, we are headed in that direction. I don't think it's a severe oligotrophication. I think it's a scary word, isn't it? Who wants to hear oligotrophication? Oh my gosh, that sounds like a bad disease. But yes, it has gotten less productive, primary production, clams, squid, perhaps fish as a whole. But it's not a huge change, I would say.
I do find it interesting, your suggestion of, well, what if we just put in nitrogen or nutrients, considering, a lot of controversy around other maybe geotype engineering. I don't know if I would even say geoengineering, but basically where we're purposely trying to influence the environment. So I don't know if it was just a question, but it was more of like, have you dealt with that kind of question yet when you presented this? Because I think the other one's like, does it violate our EPA agreements? And this is where I'm like, but that's policy to decide. And I think you're just presenting it as like a scientist. So I'm curious
Well,
what your perspective is.
honestly, I'm presenting it like a gardener. I have to put fertilizer on my garden or I'm not going to get anything to grow. Nutrients are not all bad. It's the fact that they're actually a resource. And with our being able to control the amount of nutrients coming in from wastewater treatment plants, give us a real opportunity to enhance the wild fisheries in the bay, the aquaculture industry, and also the natural habitat, the ospreys. You know, they're feeding on fish too. So I actually think we ought to think long and hard about optimizing nutrient inputs to the bay. Nutrients are not all bad.
If I can add to that too, I think that is a really, you know, it's a really important concept. I feel like I feel like humans are really uncomfortable with the idea that we are animals that live in an ecosystem. And we have been geoengineering our environment since we started running around and changing things, right? And the scale at which we continuously geoengineer our environment is outrageous, right? I'm not by any means suggesting we like dump all the nitrogen back in or like throw particles in the atmosphere, right? Introduce bunnies everywhere, whatever it is, right? But I don't think we should immediately hear a suggestion like Candace's and then be like, oh my God, no, right? And I think that we do that really quite easily because I think we're wildly uncomfortable with the fact that like we are a wild animal in the system and we are changing things all the time. And I think that, you know, nutrients are very, very important. And it is possible that we may in the future need to figure out how to manage ecosystems for that ecosystem, not as if we imagine another ecosystem behaves, so we apply the laws to it, like Narragansett Bay is not the same as the Chesapeake, for example, right? And that we may have to go against these like entrenched ideas in our head, like nitrogen's bad, we're gonna get rid of all of it. Because in fact, that's not the case. You can't have life without nitrogen. So I'm not, you know, I'm not totally ready to jump on and be like, dump, you know, how we're going to do this. But I think, and Candace, I think you've called it before, like a Goldilocks scenario, right?
Right, exactly.
And I think that that's a really interesting way and really thoughtful way of thinking about it. And I think it's, you know, we should be comfortable having those discussions and working through what that would mean and how that would work. And it's not unprecedented. There are, you know, in Louisiana, there's changes to how nitrogen and freshwater and sediment are dumped into different parts of salt marshes. And, you know, that's not working with sewage treatment plants, but it's working with industry there that's in charge of the levees and things like that. So
I think this comes down to management, right? So humans have only recently come to terms with the idea that we can impact our environment. I mean, 100 years ago or 50 years ago, we used to think dilution was the solution. You could dump however much you wanted, regardless of what it was, and the ocean would fix it. You know, it would spread it out and it wouldn't be a problem anymore. So the pendulum was swung, you know, entirely in one direction. And as we became more aware of our own impact, we started to come to terms with, oh man, we're negatively impacting the environment. And as a culture together, we are saying, wow, we really are making an impact. So we want to reduce that impact. The Clean Water Act, things like that. We did our best to try and take human impact out altogether, but regardless, we're having an impact, right? So the pendulum is now starting to swing to, you know, we shouldn't have any impact on the environment at all. But the reality is, by making that choice, we are having an impact. So it comes down to managing the resource, because just with our density and our creativity and our dexterity, human beings are fabulously adept at changing their environment. And what we should do is try to make it so that the impact is minimal but beneficial to all the organisms, including ourselves.
Great, thank you. I know some people have raised their hands, but I just want to quickly go over one question in the chat. Do you think that these findings can help inform aquaculture development, especially, you know, with other different shellfish species and kelp?
Wally, do you want to answer that or shall I?
I would think, sure. I think, yeah, more data is always more helpful. Trying to understand how much aquaculture we can put into the bay and coastal ponds and stuff is a really interesting question. And, so yes, I think yes would be my short answer.
I think aquaculture is doing fine in the bay so far. I think it perhaps in the future we'll think about improving areas for aquaculture. I think that's a possibility in terms of decreasing or enhancing nutrients, whichever is required by the industry to maximize their production. So yeah, I think we should keep our minds open with respect to that.
All right, Joseph, I see your hand. Go ahead.
Sure. Thanks. I just wanted to kind of chime in real quick in response to some of the kind of comments that nitrogen is bad. And I think there's a misconception that, well, I mean, first, my role is I'm a regulator here at DEM, so I guess I'd be one of those policy makers that you're talking about. But, there's a misconception that we're limiting nitrogen for the sole sake of limiting nitrogen, and that's not the case. Nitrogen is being limited to control DO and turbidity. Those are what we have criteria for. So, and I saw one of my colleagues, I'm sure many of you are aware of, Dave Borkman also mentioned, if we start talking about increasing loadings, you have to be careful that people don't glob onto the idea that it's, decreasing treatment at treatment plants, because there's other, impacts there. But I think it's just important for everyone to understand that we're not limiting, or we didn't limit nitrogen for the sake of limiting nitrogen. It was for the sake of meeting DO and turbidity standards. And that's why I asked the question in the chat earlier. It seems, let me take a step back. I definitely understand the point that people are making, hey, we fertilize our lands all the time. And that's great, isn't it? Well, yeah, but we don't over fertilize our lands. And it seems like we've gotten to the point where we're focusing on a select subset of species, and I don't know who's made the decision that those are the winners and other ones are losers. That's why I kind of asked the question, what are the impacts to the other species? Because I think you can make an argument that if total biomass is stable or increasing, well, this is what we should be doing. We shouldn't be picking winners and losers in the environmental equation. You're trying to get a balanced indigenous community to the effect that they are. But I just wanted to clarify that because I think there may be, I was just concerned that some people may leave thinking, oh, DEM decided to apply nitrogen limits for the sake of limiting nitrogen, and that's not the case. It's for other reasons. But just want to clarify.
Note that the
Mike, let me take this, please.
Yeah.
Thank you for asking that question. I think that was, I really wanted to some extent, I'm goading you, I think, with my talk here today to react to what we're saying. And I won't apologize for that, but I'm glad to get a reaction from you. No, we're not trying to decrease nitrogen for the sake of decreasing nitrogen. We're trying to eliminate hypoxia in waters of the Upper Bay. And there's many waters of the Upper Bay which are still impacted by hypoxia. Phillipsdale and the Seekonk River, to some extent, Western Greenwich Bay, Mount Hope Bay, we still have hypoxia problems. I'm merely suggesting that the hypoxia problem is a problem in the summertime, not the wintertime. And the two storms have put in nutrients way above what we were receiving before the managed nutrient reduction. And it didn't have negative effects in terms of causing a greater hypoxia in the bay in the summertime. So during the cold months, it's okay to release nutrients so far as our data so far suggests. If we were to go forward with this, I would suggest that we have an intensive study to verify that, to make sure that we're not going off like some loose cannon, that we make sure that we know what we're doing in terms of changing the nitrogen dynamics of the bay and hopefully improving the habitat for all kinds of fish and shellfish. So I think we would have to work with water quality managers and regulators and wastewater treatment facility people to make sure we're all on the same page before we do anything of this sort. Sorry, Mike, you could go ahead
I was
now.
gonna say, Mike, do you want to add to that?
Well, I was going to say that the quahog clam, although is a charismatic species to Rhode Island, it's also a very robust, long-lived species. So it has a history of in the bay, and they live, 30 to 50 years. So it's an excellent species to study, especially when you're looking at the influences of large system changes when it comes to things like winter, spring phytoplankton blooms, and seeing how that translates from the pelagic water column to the benthic environment. So that it's an excellent species to look at just for that fact. It's also found all along the east coast of the United States, from Florida to Nova Scotia. So it's intensely tolerant to different salinities and temperatures. So it is an excellent species just as a reference. You can get good data from it, and it has a history here. So it wasn't chosen, not that it was suggested as a winner or a loser, but just as a really good model to look.
And I can just pile on one more quick thing. I think that it's always important to have discussions and debates about these things, regardless of like where, like that we have to talk about them. We have to talk about the data that we have in hand, and whether or not we act on that is separate, but to not look at it and discuss it deeply and get all fired up about it and have all the different viewpoints in the room talk about it. I think that's really, really important. So that will make everyone understand things more and feel, more, understand things more, which is really important. And the decisions then that we all get to make then, or other people make and we live with, we at least understand a little bit more about why they were made.
Yeah, I think this was a great exchange. And, just to pull like one of the comments from David Boardman about like that, I guess kind of clarifying what we mean by nutrients. And it's not necessarily just dumping the fecal coliform loading in there, or that's part of the discussion as well. It's not necessarily degrading water quality, and it's that ongoing conversation of like what we're trying to contribute, what time, to what extent, if at all. But that was part of this conversation. And Candace, I do appreciate you even like throwing that out as a potential thing, because I feel like rarely I hear such things in research. And so I was like, oh, this will elicit some good conversation. So I appreciate that. Does anyone within the group have any more questions? Actually, you know what? I have one more final one. Candace, you already talked about like kind of some research to verify certain things. And there's going to be management questions always moving forward. But from a scientific perspective, what do you guys think some of the questions are? Like, Wally, you had alluded to maybe looking more at some of this intrusion work. Are there other aspects, like other questions we should be kind of thinking about? I mean, maybe we don't know them yet, but from a scientific perspective, what are the next kind of questions or next steps moving forward?
Well, I particularly like the eelgrass one and restoring eelgrass to the system. And I think the system has changed now in a direction that provides the light in the water column where that might be possible if we can overcome this temperature problem. In terms of restoring the upper bay to a greater quahog production, I'd like to point out that DEM is working intensively on this already. I mean, they've been able, because the bay is cleaner now and the fecal coliforms are much lower now with the managed nutrient reduction. It isn't just a nutrient reduction. We have tertiary treatment now. The water going into the bay is very much reduced in fecal coliform. We don't have as much of a bacteria problem. So they've been able to open large portions of the Providence River now to quahogging. And when I was out on the bay a couple of weeks ago, there were no quahoggers at the mouth of Greenwich Bay. There were no quahoggers at Ohio Ledge. They were all in the Providence River. And presumably the bay is now clean enough so that's a good thing. So I want to point out that DEM is already doing everything they can to enhance the productivity of the bay. But I think if we were to consider fine-tuning nutrient inputs to the bay, there should be more studies of what the effect of nutrients coming into the system in the wintertime are. And we would also have to work with the wastewater treatment facility people to see Well, can you actually do this and keep your bacteria healthy year round? That's an incredibly important thing because we really don't want those nutrients coming into the system in the summertime. So it's a multifaceted, complex question. And I think it's getting almost the right time to go after it.
I think there's lots of cool questions. More about some of the larger ecosystem responses. I'm gonna say benthic fluxes because I love them so much. It's my bias, I have to say it. So beyond the intrusion, benthic flux studies, I think more zooplankton work. Like, Candace, I think you're doing this work, but I think really trying to go after those changes and what's happening in some combined experiments, potentially like looking at grazing and warming temperatures and those kinds of things. I think it would be super fun to do the seagrass work that Candace mentioned. And then I think kind of getting a handle on the weed in the bay would be really, really interesting.
Mike, do you have any plans to take this research further?
It's been an intense 2 years, so my intention now is to finally get my thesis written and see if I can pass as a master's of oceanography, and then we'll see what the future holds.
You're going to do great, Mike.
Yeah, absolutely. Okay, well, thank you to you, our speakers, for joining us today and sharing us with your results. And also thank you everyone who participated and showed up to listen. We really appreciate it. And I hope with that, I'll send everyone off and hope you all have a good weekend.
Thanks, Meredith. Thank you, Candace and Mike.
Thanks, Wally. Thanks, Meredith.
Take care.